Nature doesn't exist in a static state. From the rotation of a planet to the chemical signals firing in your brain, every system is caught in a state of continuous, relentless motion. But our intuition usually tries to simplify this. We process the world by looking at individual moments, effectively hitting a mental pause button to try and understand a single slice of time. Standard algebra uses this snapshot approach. We plot a point for a fixed value, like y equals 10. It shows where something is for one frozen instance, but this point is blind to trajectory, making all other motion completely invisible. To understand a world that never stops, we have to move past formulas that only describe a single state. We need a mathematical language where the subject is the change itself. This is the role of the differential equation. It is the specific toolset used to calculate how a system evolves from one moment to the next. It works by defining a rate of change. Instead of just looking at where an object is, we measure the relationship between its position and the time passing by. Take a ball rolling down an incline. Its position x changes relative to time t, represented as dx over dt. This is velocity. As the ball accelerates, this derivative increases, providing a precise measurement of its speed. When an equation links current values to their rate of change, it creates a predictable rule. If we know exactly where the ball is and exactly how its speed is shifting right now, the ball's position in the next millisecond becomes a mathematical necessity rather than a guess. These same principles apply to biological systems, where predicting the next moment is a matter of public health. Epidemiologists use the SIR model to track how a population moves through 3 distinct phases during an outbreak. This model tracks the susceptible, infected, and recovered. As people interact, these intersecting curves rise and fall in sequence. The critical part is di over dt, the rate of new infections. This derivative defines the slope, showing the exact speed of transmission. By calculating this rate, researchers can project the curve forward. This allows them to estimate when the number of infections will hit its peak, providing a data-driven timeline for the rest of the crisis. These mathematical projections provide the necessary lead time for physical interventions. By understanding the current rate of spread, organizations can move from reactive observation to active preparation. This math identifies the specific window of time needed to deploy medical supplies or implement distancing measures. It tells us how much time we have to build up hospital capacity before the projected infected curve reaches a critical level. While the math doesn't stop the virus itself, it provides the structural framework for humans to organize logistics and resources against a threat that would otherwise be unpredictable. The SIR model is just one application of these rules. The same logic of change applies to how heat moves through a room, or how populations of animals grow and shrink. The notation may look dense, and the equations can become complex, but the underlying goal remains the same. In our future videos, we'll explore tools like ordinary differential equations and partial differential equations, methods designed to handle increasingly complex layers of change. Mathematics is more than just a set of values to memorize. It is a way to describe the mechanics of how one moment leads to the next. If you want to better understand the patterns of change around you, subscribe to Mathify. We'll break down the formulas and focus on the logic. Until next time, keep mathifying.